And my talk today will be about SNAD. So first of all, what is SNAD? SNAD is people, a lot of amazing and very different people. You could see their photos here on the slide, but also SNAD is a project devoted to anomaly detection problem in astronomical catalogs and databases. And during this week, I've been asked a few times, what is anomaly? What do I mean by anomaly? I'd like to stress that there are two different definitions. There is the machine definition of anomaly and human definition of anomaly. From the point of view of machine, let's say you have some data set, and then you describe this data with the so-called features, and then all normal data will be somewhere together, will be clustered somehow. But there will be some objects that we would call outliers, anomalies, that are located somewhere outside. It could be a single object, it could be a group of objects. So this is an anomaly from the point of view of machine. For a human is looking for something astrophysically interested. And what machine pointed is anomaly. It's even not necessarily an astrophysical object. It could be an artifact. Or even if it is an astrophysical object, it's not necessarily interesting because you could be wrong in your feature selection or by choosing your algorithm of anomaly detection, etc., etc. Astrophysically interesting object, in my definition, it's either something rare or something completely new, completely unknown. However, I understand that here there are also some particularities because, well, what I would call an anomaly, probably someone else would not call, because I'm interested in supernovae, someone else is interested in cataclysmic variables. So it depends on the experts also, and it depends on the task. At this slide, I illustrate the SNAD pipeline. So we are working with photometry, with the light curves. We pre-process them somehow, so we describe them with the features, and then all these features goes to machine learning algorithm. Then the machine learning algorithm produce a list of the so-called outliers ordered by the anomaly score, and then, since, as I said, the definition of machine is different, you need a bunch of experts who will look at this object, taking into account all additional external information, and decide, is it not interesting, barely interesting, or extremely interesting? If it is something extremely interesting in SNAD, we are trying to get more photometric and more spectroscopic data, classify the object, and write a publication. Important thing here is that we are trying to adopt the active anomaly loop in the process, because in case there are a lot of not interesting objects, you cannot spend the time of these guys to look at all of them. In SNAD, we developed the so-called Coniferest package. It consists of two different active anomaly detection algorithms, both based on the trees. And so roughly it works like that. In the beginning, we run the simple isolation forest, so some static anomaly detection algorithm, and then we take the object with the highest anomaly score. And there are some experts, human experts, who look at the object and say, yes, it is interesting, or no, it's not interesting. And then this decision goes back to the machine, goes back to the algorithm. And based on the algorithm we use, we either filtering the trees or we assign the higher or lower weights to the objects. So it works pretty well. We tested it on simulations and on the real data from the open supernova catalog. So here you could see the same plots. This is a fraction of anomalies depending on number of candidates scrutinized by the experts. So the green line corresponds to the active approach, the orange one to the simple isolation forest, and blue one is the random sampling. So you could see that the active approach is much more effective than two others. A nice output of this algorithm is that you could also try to use it as a targeted transient search. And it's what we did with the data releases of Zwicky Transient Facility. So we decided that we want to search for supernovae. So everything that looks like a supernovae was an anomaly for us, and all other stuff is not an anomaly. we scrutinized 2,000 outliers from 26 million light curves from the Zwicky Transient Facility data releases, and we found more than 100 supernovae. Half of them were discovered by us, so for the first time, so it was us who posted it to TNS. And what is especially interesting is that there were a few dozens supernovae that were missing in official alert stream of ZTF. Well, unfortunately, this research has been done in archival data, so we could not go back and to have a spectra to classify, but we try to prove somehow that they are supernova indeed. So we feed these guys with some simple supernova models. Well, you could see a few examples here. The light curves of some objects are really very nice. What is also important is that some of them have very well sampled early light curves. And despite the fact that we were looking just for normal supernovae, we discovered also 4 candidates in superluminous supernovae. Especially interesting was this object, SNAD 160. Thanks to our colleagues, we were able to obtain a spectra of the host, so to define the redshift and then to compare the multicolor light curves of the objects with some hydrodynamical supernova models from the stellar code. And it was fitted very well with the pair instability supernova models with a pre-supernova mass about 250 solar masses. So I think this is a really interesting object that could fit the definition of anomaly. Of course, we have a lot of other things, a lot of other objects, and we don't want to limit it ourselves to any particular class of transients. We are not searching for anomalies among the variable stars only or among the supernova stars only. We want to search for anomalies in general. And among the objects, so we found there are a lot of non-cataloged objects like active galactic nuclear, probably some candidates to luminous blue variables and can potentially explode as supernova in the future. Some of the objects we are trying to classify by ourselves, as I said, to have an additional spectroscopic observations, like for this binary system. And also in ZTF, we have some pieces of very high cadence data. So sometimes our algorithm point to this part of the light curves where you have a lot of points. And so like that, we found M-dwarf flares, like this guy with 2 peaks, and actually been inspired by the presence of so many M-dwarf flares. We even initiated a separate project devoted to M-dwarf flare search in high cadence ZTF data. Because as you know, M-dwarfs are the best candidates to search for extraterrestrial life. And of course, we have to know how active these stars are. So a couple of other examples from our last workshop, this nice binary lens and an optical counterpart of some known radio source. And let me show our favorite anomalies artifacts. So when we began this work, we had plenty of them. As I said, for a machine, artifacts actually could be an anomaly. And as a joke, well, we even created a separate web page where we store different images of different crazy artifacts. But at some point we understood that, well, we spent too much time of experts to look at these artifacts because it could be 90% of outliers. And actually, as you could see, some light curves could look as a normal variable, well, kind of. But this guy, all points here are artificial points. And then one of our students, Timofey Semenihin, he actually used these images to create a real bogus classifier. And to our features, we added an additional one responsible for the real bogus score, and now it works much better. So the blue, it's a distribution of 5,000 outliers from isolation forest before adding the real bogus feature to the feature set, and in red after we added. And you could see that the number of objects with a high real bogus score is much less now, but we still have it, and here is where active anomaly approach help us. So first time we have an artifact, I say no, and it's filter out all these guys, almost. And also let me advertise a little bit our viewer, SNAD viewer for ZTF data releases. If you are working with data releases or plan to work with data releases, I highly recommend to use this viewer written by Konstantin Malanchev, because we made a cross match between different object ID for the same source for you. There is also an opportunity to add the light curves from the Pan stars, from the Gaia. You have a cross match with many catalogs and databases of variable stars and transients. You have a fits image of every point on the light curve and Aladdin map. So let me conclude. I want to say that we should not forget that machine anomalies, machine outliers are not necessarily astrophysically interesting objects. Then probably some lessons that we could learn for future LSST alert stream, because some transients are missing. Active anomaly detection is very, very effective approach, and please don't remove human from the loop. Thank you.